Okay, welcome everyone to HO Colloquium today by Shish Lata Soni. Shish is an early career scientist dedicated to the field of solar physics. Her professional journey entails conducting fundamental scientific research in solar physics and space weather using observations and modeling. Additionally, contributing to the planning and designing of heliophysics missions. Her current research focuses on generation and evolution of magnetic switchbacks using Parker Solar Probe, Solar Orbiter, and L1 assets. Also, evolution of CMEs and radio burst phenomena using heliophysics system observatory and ground-based instruments. She is contributing to NASA's Sunrise and Swift missions, subleading the NASA Sunrise Ground Radio Lab Outreach Project. She's learned her PhD in space science in India and worked as a research associate at ISRO's Vikram Sarabhai Space Center, contributing to the Aditya L1 mission. Beyond research, she is dedicated to mentorship and outreach, guiding high school and undergraduate students in space science education through NASA-sponsored program. She has received several accolades, including the Outstanding Postdoc Fellow Award at the University of Michigan, USA, and the MP Young Scientist Award, India. So today, Shish will be speaking on CME-CME interaction, mechanics, radial evolution, and amplification of geo-effectiveness, MIRAGE. This is.
Thank you, Moshmi, for the kind introduction. Good afternoon, everybody. As she already introduced me, I'm Sheesh. I'm from University of Michigan. I'm working as a postdoctoral research fellow there. Next 40, 50 minutes, I guess, I'm going to talk about majorly talk about the CME-CME interaction topic, and also I'm going to talk about my current project, which is on magnetic switchbacks and other project that I'm working on. So let's start with the CME-CME interaction. So I'm going to talk about their mechanism, mechanics, radial evolution, and amplification of geo-effectiveness due to that. So, you all are solar physicists, and there's no need for the define the coronal mass ejections, but just for sake of completion, CMEs are significant release of plasma and magnetic field, which is originated from sun. And this is very new observation from PSP. So this is size of sun, and these images are from the WISPER instrument on board on Parker Solar Probe, and you can see the interplanetary medium, how CME is propagating into the interplanetary medium. That's huge. So, and PSP gives very, very interesting images. So that's one of my favorite from all of them.
So running difference?
Yes, these are. So, sorry. Okay, so CME is individual CME is combination of magnetic field and plasma. When it comes to CME-CME interaction, so I would like to just complete it. So CME accompanied by the structure, the internal structures. In this right side of the image that you can see, this is a magnetic field loop or flux rope of CME. And because of these that erupt or propagate into the interplanetary medium, it creates a turbulence before the CME, which is called sheath region. And as it is higher speed than the background, so it creates a shock just before the CME. And CME is also accompanied by the core and the magnetic cloud and all. So sorry. So when it reached to Earth, so CME can erupt in any direction of interplanetary medium, but if it's Earth directed, or we call it hollow CME, when it interacted with the Earth's magnetic field, it can generate geomagnetic storms. And if we talk about the intense geomagnetic storm, which has DST value minus 100 nanotesla and below than that, so most of those geomagnetic storms are because of the CMEs, or 90% of those geomagnetic storms are due to the CME interaction with the Earth's magnetic field. So what are the source or the genesis of those intense magnetic storm? So when the CME comes, it has a long duration of southward magnetic field, or we call it BZ component of magnetic field. So when this BZE component interact with the Earth's magnetic field, they interact, and because of that it creates more magnetic index into the Earth side. And also because of this compression and the magnetic and plasma thing, it creates elevated dynamic pressure, which is also responsible for this intense geometric storms. So majority of those geometric storms is because of the individual CMEs, which is just a single structure of these plasmoid. But 70% or 27% and more than that is because of the CME-CME interaction. If there are more CMEs within the shorter period, and they interact with each other during their propagation, and it creates more complex magnetic field and also more complex ejecta, which creates intense geometric storms. Sometimes these CMEs can interact with the other solar eruptive phenomena like CIR, high-speed solar wind, and etc. So those interaction can also be the reason for these intense geomagnetic storms. So with this statistical study, what we know that 1/3 of CMEs are complex CMEs. Complex CMEs, just simple terms to show that it could be a CME-CME interaction, or it could be an interaction with the other solar transients. So what are the scientific objectives that we are working on? So how these collisions of CMEs can amplify or modify the resulting shock waves and also magnetic field, which is ultimately impact the Earth's space weather and geometric disturbances. And the motivation from where we got that motivation to work on this particular scientific objective is we published just recent study where we saw there was three CMEs interacted during their propagation, and due to their interaction, geomagnetic storms was amplified as doubled. If there was only one CME, it was half of the predicted one. So that was the motivated study we recently published. So now, as we are in the solar maxima, and a study says that, like from decadal survey, it says that during the solar maxima, we have 10 CMEs per day. And if we're having 10 CMEs per day, it means like there are more chances if they are Earth-directed, or if they are having a similar orientation in the interplanetary medium, they can interact more. So where they can interact anywhere. They can interact near sun. I mean, when they are propagating, if the duration between two CMEs are very close to each other, time separation is very close. So they can interact near corona or within the corona itself. They can interact near sun. They can interact interplanetary medium in the sun-Earth line. They can interact near Earth, and they can also interact beyond Earth, but we are not into that interest to look into what happened after what if they interacted beyond Earth. So, but they can interact there too. The next question is like how they interact. So they can interact in multiple ways. So if you see this particular, here we are at the screen point is Earth. These two are stereo. So if we just imagine a CME is a huge bulb is coming out. So one CME is like this, and other CME is like following CME can have any orientation. So they can interact. So if you what's this? So in this, just imagine that this particular part is nose section of a CME, and these side sections, lobes, are the flank. So they can interact nose to nose if one CME is propagating and the following CME is like just back to that and having same orientation. They can interact nose to nose, and these interaction creates more complex ejecta and sheet because they are compressing with the same force. Other possibility could be like one CME is going like this, another CME is going to the other orientation. They can interact with nose and flank. They can interact flank to flank. Two CMEs like going to different direction. Their flanks can interact and they can create different kind of sheath and magnetic combination, magnetic field combination. Sometimes there is no direct interaction, but the one CME is propagating and the other CME is coming a little lately, but still they can compress the sheath and sometimes they can compress the sheath, and sometimes the previous CME make ambient field so smooth that the other CME can also can have different scenario what it should be if it was the individual CME. So these CME interaction can make various ways and make complex scenarios. So what kind of CME-CME interaction could be? So there are three major types. So one is homologous or quasi-homologous CMEs or interacting CMEs are those CMEs where the one single active region is erupting multiple CMEs. So, for example, if particular active region is erupting multiple CMEs within the short period of time, so there are more likely chances that they are having same orientation. So the interaction called homologous. Difference between homologous and quasi-homologous is if two CMEs are within the period of 7 hours, we call it homologous. And if there's a separation between two CMEs is more than 7 hours, 7 hours to 14, 15 hours, then we call it quasi-homologous events. The other one is sympathetic. Sympathetic CME-CME interaction are those interaction where two active regions are close enough, like not that longitudinal latitudinally separated, but so one active region is erupting CME, and because of that eruption, it triggers the other active region magnetic field also, magnetic field loops. And because of that, there are two CMEs erupted together and they become complex ejecta, and we call it sympathetic. The other one is analogous. Analogous interacting CMEs are those CMEs when there are two active regions in this visible solar disk and they are fairly separated by longitudinal and latitudinal. But as CMEs are huge structure, even though they are separated longitudinally and latitudinally, if they are propagating into the interplanetary medium, they can also interact. So these are three different types of CME interaction. And so as I said, like they can interact in various ways, flank, nose, and etc. So these three types are also majorly dependent, like how they will interact when they propagate. So to observe them, we have a big network of space-based and ground-based observatories. So what I'm using Parker Solar Probe, Solar Orbiter, SDO, SOHO LASCO observation, wind to get their in situ observation, wind is discover. We can also observe them in radio observation. So I'm using ground-based observatories, radio observatories as well. If you're familiar with the eCallisto network, so it has a very wide network which is observing low frequencies, low radio frequencies. So it's also very good signature, very good observation to look into the CME-CME interaction or CME observations. Okay, so apart from them observing them using observation, we can also observe them. We can also study them using models. So one very important thing that we have to encounter when we are looking into their interaction, it's their orientation. And on the surface, we get GCS model is very helpful. GCS model will give you the latitude, longitude, half angle of CME, height, aspect ratio, tilt angle, and speed of those CMEs. So for this, we have to have at least 2 viewpoints or more than that. So if we have Soho-Lascaux observation from Earth view, and stereo, it's somewhere like from 30 degree and more. So we have 3D view. So stereo B is not working anymore, but mostly we will be okay to simulate or fit those CME's orientation by using stereo and Lascaux viewpoint. So if you are seeing a CME as erupting and from there, and you have 2 viewpoints, so you can have easily you can model or fit how big CME is looking, or what are the orientation of that CME or tilt angle especially. So this is very useful. And the other model what I am using so far is Euphoria. Euphoria is a 3D MHD global simulation where we can simulate their magnetic field and their speed density and the plasma of CME. So this is one of the example of a model CME, how we can look into the interplanetary medium, the density and speed of CMEs. And for that, we are using EUV images, HMI, and PFS model to input CME cloud into the 3D MHD. Here I would like to just show up one case study, what I just motivated for the CME-CME interaction board. So that particular event was occurred on November 2021. So majorly, the community was thinking that there was only one CME. CME3 was the major CME. Because of that, we got the intense geomagnetic storm, which was around minus 42 nanotesla. But when myself and my team, we were working on this particular event, this third CME, we found that just before this CME, there was 2 partial halo CMEs, and those were interacted with this. So this right side, you can see this is Lascaux point of view. I mean, we are looking from the Earth side, and these are the stereo. Stereo was at that time, it was around 50 degree. So you just imagine that we are looking something from straight from the Earth side, and something is like from the 50 degree. So you can imagine this. You can imagine the orientation of CME. So this is very good example of the third CME-CME interaction, where I said like analogous CME interacting CME, where 2 different active regions, which is well separated by longitudinal latitudinally, they erupted CME in very short period, and those CME interacted when they like propagate into the interplanetary medium. So this particular one was halo CME, like purely Earth directed, but these 2 are partial. So these 2 CMEs were interacted nose to nose, but the complex structure of these first 2 interacting CME was interacted with the third CME as flank to nose interaction. So if you imagine, these 2 have very similar orientations, and then when this combined structure merged with this one, last one, it was flank to flank interaction. Sorry. So we looked into the other white light observation from stereo and Lascaux Soho 2. So these 4 images from the Lascaux, and you see this is first CME. Just after first CME, there was second CME erupted, and those were very close to each other as time eruption time. So they merged very close to the sun. And then when these 2 CME was erupting, like propagating, third CME was initiated or erupted, and it was like full halo, but that was it. That was interacted with this particular structure. And as I told you, that stereo was around 50 or 50 degree. So you can see this first CME was erupting, and the second CME was erupting, and it interacted with the first one, and the merge structure was propagating. It is stereo AH1 images, and first complex structure was propagating, and the third CME was erupted, and later on at HI2 helioimager 2, we can see this first structure This is CME 1 and 2. This is third CME, and at somewhere around 45 solar radii, they all are merged together. So this particular thing is a high time profile of LASCO Soho, where it was just saying that first two CMEs was interacted around 25 solar radii, and if we just make it linear high time profile, you can see that this merged structure should interact with the third CME somewhere around 50 solar radii. So these are the observation what we got, but we were not very sure. So we have to model it. So Euphoria helped us to look into how it should look like if we model them with the initial parameter of CMEs. These are different viewpoints of interplanetary medium that we can see. So this is from that zero plane. This is arbitrary plane, something tilted here, and this is the other view. So with all those three observations, what we got is they are interacted very well close to these observations. So instead of 25 solar radii, these model CME interacted at around 22 to 22 solar radii, and instead of 50 solar radii, with the model, we found that those were interacted at around 45 solar radii, 40 to 45 solar radii. So model gave us very similar results what we got from the observation.
What's the difference between what observations does the model take as its input? Just very close to the sun, and then you let it propagate.
Yes.
You don't update it with observations as the CME progresses.
Yes, so we just have initial parameters. So their speed, the CME speed, their longitude, latitude, and their orientation.
But you just choose. Do you choose that at some distance from the sun?
Yes.
Or?
So for Euphoria, we can start it from 20 solar radii. So we put all the initial values at how the CME look like at 20 solar radii, and then we can just propagate it into interplanetary medium. So till 20 solar radii, we have clear observation through stereo and solar Soho, LASCO Soho. So those were correct by that distance.
And are you using the same parameters that you get from the GCS fitting?
Yes.
Is the way that you put it in. Okay.
So for this, for GCS fit, we need observation from Soho, from LASCO and SDO. So of course, so the orientation of CME will get from the GCS, and then we put into this Euphoria MHD models, and then we can propagate CMEs and get their in situ parameters at any point in the inner helisphere. So now it comes into how geo-effectiveness can impact of those interactions. So these are wind parameters. So black plot is wind observation, and so what we did, so the community was thinking there was only one CME. Third CME was the major CME, which was responsible for this geomagnetic storm. So what we looked into, we have model results now. So we looked into the only third CME results, and what if there was all three CMEs. So blue curve here is for all three CMEs, and red curve is for only third CME, and of course black is the real observation. So if there's empirical equations that we can, if we have velocity magnetic field data at Alvin point, we can estimate the DST. So we have empirical solution for this. So this yellow plot is just simple pattern equation where we used Alvin point observation to estimate the DST value, which is very similar with the observation. And then we used Euphoria inputs, Euphoria modeled in situ parameters for 3 CMEs and just for all 3 CMEs and for the last CME only. And based on our observation and estimation, we found that if there was only third CME, the estimated DST would be the half of what we observed. And if there was all 3 CMEs, the estimated CME, estimated DST is very similar what we observed from the event. So with this case study, we concluded that these 3 CMEs evolves into the interplanetary medium, and that's how they double their geo-effectiveness. But this is not the only case. This is not always the case that the interaction of CME can enhance the geo-effectiveness. If the interaction is not well oriented, they can also reduce the geo-effectiveness too. But we don't have any case study on that. The very important and very exciting event that we are working on nowadays is the May event, where the aurora was witnessed from lower latitudes also. So this picture is imaged by me. I was in Michigan and it was so beautiful that day. I mean, I can see it from my window. So that was beautiful. On this particular event, I also published an article recently in 24th of Feb, last week. So what does that particular event is? So entire, I guess in this department also, are you guys working on this particular event? All the solar community is working on this event. So I think I'm very sure that somebody is working on this too. So the community is like very well, not so into one page that how many CME was interacted for this particular event. So from 8th to 13th of May, there was multiple CMEs erupted, or I can say like from 5th to 13th of May, there was so many CMEs were there. And this is very quick run from WSA Analyst, where it was saying 11 CMEs were there which interacted. But going back and forth to the SDO images, SOHO LASCO images, and stereo, we tried to finalize like how many CMEs were there, which is based on their initial observation could be interacted during their propagation. So we finalized that there was 9 CMEs. These first 3 CMEs were very well diagnosed by the white light observation. This 4th CME was, if you see their longitude and latitude, it was very away from the other CMEs. Like it is very off. So it was from the, I guess I don't have that solar image, but it was from the other active region, and it was very much off directed from the other CMEs. So community is like saying that this particular one is not at all interacted with these other CMEs, but when we modeled them, we found that there was a very slight flank interaction that is not majorly changes their sheath and magnetic field, but if there are any possibility of making it complex, we just keep into that account too. So after all our discussion, we finalized that there was 9 CME. So our other team of our this particular event, they are saying there was only 6 CMEs, and what was the reason of their saying why they are saying that? So these are the in situ parameter, in situ observation. It's a wind observation. This black one is wind observation, where we are looking into velocity, density, Vx, Y, Z, total magnetic field, and DST value at the second last panel, and this is plasma beta. So if we just look into this particular one, so this is first ejector that we got. So this is the first shock arrival at Earth, and then there was what should I show? Okay, see the BZ. So there was one rotation, the other rotation. So this is sheath region, and there was one rotation, two rotation, third rotation. So till this, what we were thinking that it could be because of CME 1, 2, and 3, and then there was another. I think I should make a line for this, but not in this plot. But this particular plot, this particular rotation in magnetic field is because of the CME 5, and this one is because of CME 6. So we have 1, 2, 3 till 6 were there. So earlier we were thinking that this particular part is because of CME 1 to 6. Earlier we were unable to see this structure in the enhanced velocity. We were not able to plot this or match this enhancement velocity because of all 6 CMEs. So then we added 3 more CMEs, which is erupted on later in 9th and 10th and 11th of May. And we were very well able to do this. So this enhancement is because of last 3 CMEs. This is not like at this moment, you cannot see this very well correlated with this because of we are still working on this modeling stuff. So if we initiate these value a little bit earlier in the initial fit, then we can be easily good to fit them earlier. So that was the reason we end up with the 9 CMEs.
There is a question on this time. What is CME time in that table? First appearance in C2 FOV.
Okay, so we started with the 8th of May CME. So 8th of May CME arrived at around 11th of May, I guess. Yeah, later in 10th of May.
I think he's asking if you go back to the previous
In the
table, in this
yeah.
table, when you say date and time there, what is that? What time does that correspond to? The first time you see the CME in
Yes.
the LASCO?
This is the first appearance in LASCO C2 coronagraph. And this is Elvin point. Yeah, so we are still working on it and still trying to get the DST value observed. But still we are a little far. That's why my comment was CME interaction can enhance the geo-effectiveness and also can reduce the so we are not very sure that what happened with this. So we're still working on it. That's all about CME-CME interaction. If anybody have any question, then
I have 2 questions. One is your classification of homologous, analogous, and sympathetic.
yeah.
And so, what is then recurrent? Where does it fall? The recurrent CMEs.
Current CMEs?
Yeah.
Okay.
Is it homologous or analogous?
So current CME, if I'm not using the CME4, then it's homologous. One active region is erupting all those CMEs. Or we can say that these are the quasi-homologous because the time difference between all 5 or 6 CMEs are like little more than 7 hours. But if we take the CME4 also, if you remember the table, yeah. So the longitude and latitude is like quite away from the other. So that is from the different active region. So if we take that into account, then it becomes an analogous interacting CME event.
Okay, one more question. Okay, Joanne, you go ahead.
Yeah, I have a question on the plot you have of the geo-effectiveness of the 2017 CMEs. Yes, that one, thank you. Just so I understand that bottom plot, I'm not sure what CMH is. Is that DST
Yes.
that we're looking at?
Yes, so DST is 1 hour average value of CMH. CMH is 1 minute data.
Okay, thank you. And it looks like the empirical model does a good job of fitting the, down to the matching very well the DST negative values. And then you point out that the all CMEs does a better job of showing the negative BZ.
Yes.
But it still doesn't capture all of the negative BZ. So I'm a little confused. It's underestimating both the duration and the extent of the BZ south, and yet the empirical model is a good fit. So I just wasn't sure why you have those differences. Is the model, because I thought the model was including some of the CME.
Okay, so the reason behind it, so empirical model is using density also, and the density which is observed at Elvin point. So if we combine velocity, density, and BZ together, the empirical model will give you very exact value what we observed. But Euphoria is not very well to estimate the density value, to model the density value at Elvin point. So because of that, this discrepancies in the estimated one. So we gave this particular reason in our manuscript, like why we are not able to estimate this because of the density is not very well understood, estimated due to the euphoria.
Okay, great. Thank you.
Can I ask a follow-up on that?
Yeah, please.
So if I understand rightly, Euphoria is taking as input the CME observations back at 0.1 AU, right? 21
2020 hours, right?
RF. And then it's doing the full MEP simulation of the propagation. And that's what you're plotting in the red and the blue for those two cases. The empirical model is using 1 AU observations, measurements of density, magnetic velocity, and using known relationships or sensitivities of those values in relationship to the EP type thing you're looking at, right? So you would expect it to be very similar because it's been fit empirically to match that, because it's using 1 AU observations as opposed to Euphoria, which is using observations from much further back to drive a model. Is that right? Okay.
And you have two more questions online right at the beginning of your talk, the condition dart. Is it from my computer also? No.
Yeah.
CMEs?
Oh, should I
you
just
want- Okay, please.
Yeah, so okay, so basically I have a cadet working at West Point with me on what the CMEs look like when they arrive at the Earth. And by that time, of course, several CMEs have merged. My understanding is that at least the first three had merged into kind of one by the time they hit the magnetopause. But I mean, we're having, some similar difficulties demarcating what counts as a distinct CME. I guess two related questions. One is very simple. Is there a standard way to demarcate the trailing edge of a CME that's past ACE? So like, for example, if I just look at the density, do I just see where the density looks like solar wind density again? Okay.
So you're saying like, what would be the good way to look into this different CME component at 1 AU? Is it?
So that's one question. Like a much simpler question is just for any CME, say that has passed ACE, and then it's mapped to the magnetopause. How do I specify what the trailing edge of that CME is? Like when the return to the solar wind happens.
Okay, so the very easy way to look into the velocity. So if you are at the trailing edge of CME, you can simply see this dip, the slightly dip into this velocity. So this is the one way. And if you are at the trailing edge of CME, you can also see your plasma beta is recovered. It's not negative. So you can also see that too.
Okay. So yeah, those things happen in different locations. Anyways, it's a little bit unclear like where to draw the exact boundary, but I guess I'll ask the more interesting and relevant question, which is, again, if multiple CMEs merge and ACE witnesses some complicated signatures of magnetic field and plasma density and so on, is there some way to trace back sort of like, what features came from which CMEs? For example, like maybe one of the CMEs dominated the magnetic field signature or something.
So all the CME, complex CMEs are behaving differently. As I said, like they can, if they are merging together at very, very close to the sun, and the merging structure is propagating into the interplanetary medium, it's very hard to distinguish those structures at 1 AU observation. So if something is already merged earlier, so we cannot distinguish their sheath or their magnetic cloud at 1 AU. But if something is, some two CMEs are interacting at near Earth, then it's easy to distinguish them apart. Again, the type of interaction, how they are interacting to each other, that also impact a lot how we can distinguish them at, or how we can identify them at 1 AU. So we can trace back just to look into the interplanetary media. To the white light observation. That's the easiest way to look into what's happening when they are propagating.
Okay, perfect. Yeah, that's very helpful. Thanks so much. It was a beautiful talk.
I have a quick question. So when for your if your model, the input from an inner boundary at the 20 solar radii, it's the GCS input parameters you put in?
Yes.
Okay, but it doesn't have any magnetic field information.
No. So we have magnetic field information with HMI or EUV images, HMI especially. So,
but how did you put it in there? Based on what did you put in as a magnetic information?
We can put
the field directions of?
We can put, that is not done by me, but
Okay, I can ask you later.
yeah, that is done by my collaborator, but the input parameter of magnetic field of CMEs can be used with the HMI data of active region directly.
So you do put some magnetic.
Yes, of course. That's how we get this.
Yeah, the BZ.
Easy and
Okay,
the plasma data, etc.
I'll ask you in the board later.
Yeah. You were asking something, sorry.
Anyone have anything? I was asking about geo-effectiveness. So geo-effectiveness depends on the cycle. So this cycle, one hemisphere is more geo-effective, and in the next cycle, other hemisphere is more geo-effective. So the increase or decrease in geo-effectiveness we are proposing here from the CME-CME interaction is on top of that. Like if it was less geo-effective, it makes more geo-effective. Can it be even more geo-effective than the more geo-effective cycle?
Look into that scenario because there are very few case study on this, and also as I said, like all the CME complex events are different to each other. So we are having so far we don't have any statistical study on like which is more effective. So should I go for the one? Okay. So other thing that I'm working right now is magnetic switchback. So I started working on this during my second postdoc when I switched to University of Michigan. So me and my team there in University of Michigan working on the generation and evolution of magnetic switchbacks and also their impact or their role into the coronal heating and solar wind acceleration and heating as well. So what are switchbacks? So switchbacks, as the name says, that something is switching back toward, like backward again, and then coming back. So switchbacks are the large amplitude fluctuation in the magnetic field lines. BR reversals, we can simply say. And wherever there is BR reversals, because of their alphanic structure, there is enhancement in the velocity as well. We can say them as a short-term current sheet crossing, but these are not current sheet crossing because the total magnetic field is constant during this period. So if you see this, so this particular blue one is the BR, and it was negative, and then back to it goes to the positive and coming back to the negative again. So this particular one is called switchback. In the community, the definition of switchbacks is not clear. Half the community is saying that if there is any fluctuation in the BR, it could call as switchback, but we define it as if there is 90-degree fluctuation, just reversal, positive to negative or negative to positive, we call them switchbacks. Otherwise, it's just a fluctuation in magnetic field. That's it. So the question arises that what are the source and generation mechanism of switchbacks, and also do they evolve with the heliocentric distance or not? And if they evolve, how they evolve also. So for that,
What was the red curve?
This
blue is the BR. What is the red?
That's three other components. So BR, B normal, and BR and G.
And the total B is not changing.
Yeah, in this plot there is no total B, but total B is not changing. It's just a constant. Okay, so another definition what we gave into the community is there is a switchback if it has 5 distinct magnetic regions. So one is the quiet period. This quiet period is basically ambient solar wind, and transition period where this magnetic field is changing towards the spike, and the spike where the BR is situated in the different polarity for a while, and then come back to the trailing transition region and the quiet trailing region. So if any structure in solar wind has these 5 distinct magnetic regions, we call them switchbacks. So what we have, why we are working on it. So scientific objective of this is investigation the generation mechanism of switchbacks and determine how the switchback magnetic energy reduces with heliocentric distances. The motivation comes after my advisor's first paper on switchbacks, where he he stated that the magnetic switchbacks can heat the corona, solar corona. And that was biggest statement when he stated that. And what he determined with those observations was he looked into 8 PSP solar encounters. Encounters means when the PSP was very close to the sun. So if you take the perigee of PSP, when it was like closest approach of sun, and then add 7 days plus and minus, I mean, before and after 7 days, the 14 days is like one encounter. So at that time, PSP is observing very high resolution magnetic field. So that's how it observed many switchbacks, because switchbacks is basically few seconds to minute observation. And it's very short observations. So because of PSP, we observed many switchback kind of structures. Before PSP, there were very few observations which looked into which observed these switchbacks. So one observation through Ulysses, another one is from the Hellers. So these 2 observations on magnetic switchbacks before PSP, but after PSP there were lots of switchback events what we found. So in this particular study of Moshtaba Kantaki, what he found with this first 8 encounter of study, that the switchbacks evolve and they reduces magnetic energy, and because of this magnetic energy reduced, and it transformed into the kinetic energy and heat. So that's how it could contribute to the coronal heating. But as PSP has more encounters, so recently we published one other study where we looked into the 14th encounters observation of PSP, and we found that there were few times when PSP was below the corona. I mean, PSP was under the corona, below the alphinic surface, and so in total, so I guess, yeah. So for 20 hours. Within this 14 encounters, for 20 hours, PSP was observing magnetic field and solar wind below the alphinic surface. And for these 20 hours, we couldn't find any switchbacks. So just the normal logical thing is like, if there is no switchbacks in below the alphinic surface, below the corona, so it cannot directly contribute to the coronal heating. Like if there is no switchback in the corona, how it could contribute to the coronal heating, right? The other big outcome from this study was more than half of the community, 50% of community was saying that generation mechanism of switchbacks could be because of the magnetic reconnection, which is happening over the solar surface. So because of this magnetic reconnection, the magnetic field lines become kinked, and those like propagate into interplanetary medium, and we observe them through PSP and all. But if that's the case, if that is the generation mechanism of solar, there's a magnetic structure or these switchbacks, then we should have these structure more when we go close to the sun. If we are observing those structures below the alphinic surface, we should have more switchbacks, but we couldn't find any single switchbacks below the corona. So that was given another hypothesis for what could be the possibility of generation mechanism. So the community is saying 2 generation mechanism is possible. One is in situ, other one is ex situ. So ex situ is because of the magnetic reconnection on surface. In situ is like something happened on the solar wind itself. It could be because of the velocity share. It could be because of the KH instability. There are many other possibilities, which is indicating their generation mechanism is in situ, not the ex situ. So this is just a hypothesis given based on the observation. We are still working on like what could be the reason for the in situ mechanism of this. The next study, what we have just published, not just published, it's been few months. So in this study, what we have shown is, this is majorly, so previous study is based on the generation mechanism of it. This study is about the evolution of these magnetic switchbacks. And what we have done in this is, we looked into the same solar plasma parcel from 2 different locations in the solar interplanetary medium. So one is from the PSP, when the PSP was around 25 solar radii, and the other observation from the solar orbiter when the solar orbiter was 150 solar radii. So, so there was one misunderstanding when we were talking about this particular event. So PSP and solar orbiter was in this particular time when we were observing it. It was not in the same HCS part. So it was like different side of heliosphere current sheet. So what we are observing here, it's not the same solar wind patch what we are observing at solar orbiter. But still, how we validate this comparison? So this part is actually tricky when we were looking into the switchback structure from two different locations in the heliosphere current into the interplanetary medium. So first is these structures are very small, and tracing one small structure from one location to other location it's very difficult. So one tricky part was that, and the other one is lack of observation from solar orbiter and PSP. So we looked into 12 periods where the solar orbiter and PSP was aligned together, and we end up with and we also need to look into like how it propagate. So we have to have a closest observation and the farthest observation. So based on these 12 observational periods, we have 7 out of them where the solar orbiter was far and the PSP was fairly close, less than 30 RS. And then we looked into the BR reversals. Those 7 encounters should have BR reversal. But when we looked into the available data, so we had only one single period, alignment period, where there was available magnetic field and plasma observation. So that's why we end up with this particular scenario. And the validation of comparison, like one can say that we are looking into 2 different heliospheric observation, solar wind, it could not be this, we cannot say anything with this evolution. But when we trace back these structures back to the sun, we found that the magnetic footprint identification like very similar for those two. And also we looked into the plasma alpha proton signatures, which can also say that which can also prove that the generation of those solar wind patches are very similar. So these are 2 valid points why we are doing that comparison. What we found here. So as I said, like for one single structure is very difficult to follow up. What we have done is we looked into the solar switchback patches. So switchback patches is like multiple switchbacks within short period. So multiple BR reversals. We call it switchback patches. So you see that there are 1, 2, 3. This is not the case. I mean, just a illustration, but we have observation for this. So this is PSP observation. And when we looked into the solar orbiter, we saw that these BR bendings are much less. The pressure was very less. The magnetic pressure was less. And also the bending, the BR reversal, number of BR reversals was also very, very less in the solar orbiter. So in this particular study, we found 4 patches in PSP, but no single patches in solar orbiter. We call this is not as a patch, we call that a microstream. Microstream is another creature, as we were discussing today. Microstream is another creature which is very similar to patches or individual switchbacks, but there is an enhancement in the velocity, background velocity, and also the density enhancement. So this background blue is indicating the background velocity enhancement. So if the same structure was observed in the same heliosphere current sheet, we thought that it is very similar to what we observed in solar orbiter. So with this study, what we concluded that this switchback patches evolves as microstreams. It means they are the magnetic field energy. Magnetic energy is reducing, and it's converting into the velocity, the kinetic energy or the heat energy. So as the background velocities increases, we concluded that as switchback patches is converting or what do you call it? Evolving as microstreams, they are contributed to the solar wind acceleration. So that was again a case study where we looked into 4 or 5 patches just for one alignment. But now we are working on their statistical study where we looked into all the PSP observation, all the patches and microstreams observed at PSP and solar orbiter, and looked into what exact contribution to this evolution to the solar wind heating and acceleration. So that is all about switchbacks. If you have any questions.
Good question. That's really interesting. The statistical study sounds fascinating. Do you have any idea now, or do you think that you will be able to resolve it with the statistical study? Because with Parker, you'll be able to, look at a lot of different passes and different distances from the sun. Will you be able to see some sort of transition region relative to the alpha zone where you go from the one to the other, where a clear categorization of switchbacks would be one at one place and in another place further out, a clear categorization. Here you're comparing 25 and 150. Are you going to be, what kind of height analysis would be able to do to really pin that down?
If I get your question correct. So when we are identifying or when we are defining switchbacks, so we are also taking account this spiral, Parker's spiral, and what's the angle of that spacecraft, like how it's observing the magnetic field lines or radial magnetic field lines. So when you account that too, then you don't need to worry about where we are observing them.
Now, yeah, my question is, it's sorry, it wasn't very clear. What I'm seeing in the orbiter observation is what you're calling microstreams.
Mhm.
Am I right that if you looked at Parker observations from further out, you would also see microstreams?
Yes.
So is there a height, a distance from the sun where you see only microstreams and a height where you see only switchbacks and an overlap, or is that at all known?
So the study, what we are doing right now, the statistical one, it's very surprising. We are having more microstreams when we are observing from the Parker solar probe.
Closer in, or
Just encounters. So when we are looking into Parker observation, we're just looking into the encounters.
Right.
I mean, till 70 RS, 70 to 80 RS.
okay, so it's 70 hours. Okay,
Yes. So yeah, we found many microstreams.
that's
There.
at the higher heights. Is there a place though where you see where the microstreams dominate compared to the switchbacks in Parker?
If I could show you that too. Is that, yeah, this one. So this is very initial results what we have presented in AGU last this December. And if you see that majority, when we are just looking into PSP, majority of microstreams and SVPs, and when it comes to individual switchbacks, we observe them at 30 to 50 or 30 to 45 solar radius. But this is not the reason. So what my explanation for this majority of these observation at this distances, because if you imagine PSP is, so this is sun, PSP is going this way. So the perigee of observation is very for a short period, but we are having 30 solar radii observation from this way also and that way also. So we have double observation from these two distances. So that could be the reason of having more number of observation that time, and not more majority of this period. But I can't say anything like.
But it's interesting because they're similar distributions, and I was having in my head from that last case study that microstreams were process switchbacks, but they're co-located, is what that's showing you.
Yes, so that's why we are working on a statistical study, because that was just a single case study. So we cannot just conclude any hypothesis with just based on one single case, right? So we are still working on it, and we'll see how that count. Yeah.
So can I
Yeah, please.
confirm something? You're saying you don't see any switchbacks within this alpha radius.
So far, no.
So you see more after go out.
Yes.
Well, that's interesting.
That's
I think it's alpha.
So there was, if you know Marco Belli,
Mhm.
yeah. So he said in one PSP meeting that his student found few switchbacks below alphonic surface within the corona, but there is no paper out, so I'm not sure. And he said just recent encounters, so we don't know. So we'll see. I guess 19th or 21 encounters somewhere.
And what's the volume of data below the alphane surface versus the volume of data above it? You probably have a lot more above it.
So recently, PSP went very, very close. So we have long duration period below the alphanic surface. So
But if you counted up all the data Parker's ever taken, subalphanic and superalphanic, much more superalphanic.
much more, yes. Very, very few, 20 hours below alphanic surface. So 20 hours like very less compared to all observations that we have from PSP. Yeah, so that's all about the switchbacks. The other projects what I'm working on is few. So one is we are working on a mission concept where my advisor, Moshtaba Kantapti, is PI of this mission, which is called Space Weather Investigation Frontiers, SWIFT. The concept is to having 4 tetrahedral spacecraft configuration at L1 point and X7 point, so that the separation of these spacecraft is about 1 AU from each other, and that's how we can resolve the small to mesoscale structure of solar wind. And that's really good, interesting study. To just validate this concept, we recently published a paper where with the awesome model, the Chip and Nishtha was working together, and they have shown a very good modeling simulation results that how this configuration can help us to resolve these small or mesoscale structures with this. So this is one thing. I'm working as a science team on this. So we are working on more and more events, how that can help. The other one is Sunrise Space Mission, which was expected to launch in 2024, but it's delayed, and now it's going to be in 2026, hopefully. So this is another very interesting configuration of space mission, where it's very costly if we need to make a big solar disk in space. So the concept is to having 6 cube satellites together, and each CubeSat is having 10 kilometer of aperture of a solar radio dish, and it's so altogether 6 CubeSats. They are making an artificial solar dish like this, and it is going to observe low frequency radio signals from sun. And with this, what I am doing, as it is not launched yet, so what I'm doing is I'm co-leading the Sunrise Ground Radio Lab, where we are designing dual dipole antenna and also designing LWA. I'm over time.
Yeah.
Okay, just one more slide. So we are designing LWA and dual dipole antenna and trying to make similar scenario what is happening in the space, and we are comparing the space-based and ground-based radio observation. So for dual dipole antenna, we have 2,500 students team together. They're working on it, and for LWA, we have 35 plus engineers from the unit itself. So yeah, we have big team. That's it. Thank you.
Okay, thanks for clearing up. More questions and comments, and from online also, please unmute and ask. Anyone from here?
If no question, suggestions.
Suggestions, comments, suggestions from the hall, from the online.
Thank you.
I have a question about the CME-CME interaction and the GCS model. How certain can you be that what you see is not just an effect of projection effects? Because it's it's very difficult, right? And also you were also showing distorted fronts, which you can't fit with the GCS model.
Yes, there is very much chances to having errors on this. And when we are working on the very recent event, the May event, not solar orbiter, stereo was just 30-degree apart. So if you are seeing from the sun earth line, from the earth or 30-degree apart, it's not showing much changes. So it was really difficult, and there are lots of chances to having errors too. But but we are limited with the techniques.
I'll do a follow-up on that, because that's something that came up in the punch meeting as well. So if you have two CMEs and they're passing in, when you see it, it seems like they're passing through each other. You could have, of course, one in front of the other, and you don't really know, right? Because of the projection. But if you have punch and you have polarization data to show you where along your line of sight these fronts are, you can disambiguate that, right? So that's going to be really interesting to compare to the models.
That's why all the solar community is waiting for punch.
Go punch!
Yeah.
Anything else? If not, let's thank our speaker again. Nice presentation.
We're glad I was able to come.